Okay, good deal. Well, welcome everybody. So today we are going to uh, start, you know, I guess we've gone over the basics of understanding how to read code and how to write code, and now we're focusing on the final uh, piece that we need to know for developing our tech lead skills, which is how to understand architecture. Um, there are various different types of architectural patterns that we can use um, to solve the problems that we have, and that's ultimately what we're aiming to do is to solve problems. We're going to, over the next couple of sessions, move to the softer skills instead of the specific technical skills. And so we need to understand the constraints that the customers have and the requirements they have for the problems that they bring. What is their workflow? How many users do they have for their application? What performance requirements do they have? Are there any technology limitations, like what operating system they're using, or what kind of computers do they use? Where's it going to be? Where are the users based, and is that different from where the computers are based? And are your users, in one place, or are they worldwide? How educated are they? What development resources do I have for what I need to implement, and what other concerns do they I mean, there's a bazillion questions that you come up with when you start to address what the needs are of the users, and the answers to those questions can easily change as your product development moves forward. So we also need to make sure we understand how, or we need to be concerned with how flexible the system that we're building is. Can we adopt a new architecture, or will we be locked into the architecture that we choose from the beginning? And that might be a problem. Because, for instance, the system that I work on, it's a desktop application, and now we need to move it to the web, and that's not easy to do. So we are effectively having to rewrite it from scratch. Okay, so all that being said, let's look at our architectural options that we have. In general, there are 5 primary architectural patterns that we choose from when we're building a new system. Within each pattern, you can be more specific, and they may well have sub patterns, but we at least need to know the primary high-level architectural patterns so we can make an informed decision about how we want to approach any given problem that we have. So we start with what's called a layered architecture. This is the most common one that that you find out there in software world, because it's the easiest to understand and the easiest to implement. So let's take a look at what that looks like. Okay, so you can see each part of the application is divided up into a specific layer that manages the piece that it's concerned with. There's a strict hierarchy of relationships. Each layer communicates only with the layer that's adjacent to it. If some message needs to be sent to a non-adjacent layer, then it needs to go through a layer that's adjacent to it. So for instance, if the persistence layer needs something from the database, or well, let's say the user interface the presentation layer needs something from the database, like a customer record needs to, someone wants to display a customer record on the UI. It's going to have to send the request to the business layer, which is it's going to have to then go and send the request to the persistence layer and pass that on to the database layer, collect the data, and then pass that data up through each layer to get to the persistence layer. So as you can see, it can generate a lot of noise, and developers are tempted to just circumvent all the noise in between and start writing code that connects directly to other layers. And that's how you start developing your proverbial big ball of mud architectural pattern, which is really not a good one. So maintenance will quickly become a nightmare, because you change something in one place and it's going to affect stuff all over. You're solving what do you call it, the whack-a-mole kind of bugs. We've all seen the big ball of mud architecture, and it's a mess. And it usually started as a layer architecture that got out of hand. It takes discipline to keep a layered architecture properly structured. So we'll look at an example. Say a business user needs to retrieve the customer information from the data repository. So your customer screen was going to get the request from the user. Well, it doesn't know where the data is or how to get it, so it forwards it to this delegate module, and that module knows how to talk to the business layer, and so it will send a message to the customer object in the business layer. That object knows how to request data, so it sends a request to the customer data access object, and since it knows the business rules, it also knows that a separate order object is going to have to be created as well. So it sends a message to the order data access object as well. And so those data access objects know how to communicate to the database, so they send their message to the database. And so it goes and gathers up the needed data, which then gets passed back up the chain to the customer object, and then to the delegate, and then back up to the screen. So implement this kind of architecture, you might say use Angular or React on the screen and send a request to a Spring or Spring Boot business layer, and then pass that along to like a Hibernate layer that's going to talk to the database. So that's kind of how that sort of thing would be structured these days. So let's consider the trade-offs of a layered architecture. It's really easy to build, it's easy to test, and it's easy to understand. So you don't have to really spend a lot of time training up your developers. And that's why it tends to be the first approach most developers adopt when they're working on a new project. The problem is that it's not very flexible. The layers have to be very strictly maintained, and that can cause frustration when some component needs to straddle more than one layer, and it's not scalable. When a layer gets to be too big, it tends to start becoming a God object, and that quickly steamrolls into your proverbial big ball of mud. It's hard for developers to maintain the separate layers as the system complexity grows. Also, the performance can be limited because the request is going to have to pass through all the different multi-layer bureaucracy, I call it. Each layer has a direct relationship with the adjacent layer, and so any deployment is going to be an all or nothing thing. You can't just deploy one part of it. You're going to have to put it all in one unit. So some things to consider are that, first there's a risk of having a number of these pass-through functions whose only purpose is to pass data to the different layers. That can bloat the code and slow your performance. Also, your layered architecture, it generally lends itself to a monolithic application. So, if you've got a program that requires an installer, it tends to be a monolithic application. Everything is all together in one. If you need things to be more flexible than that, then consider a different architecture. Say, for instance, an event-driven architecture. Okay, so that's effectively a distributed asynchronous architecture pattern. It's event-driven and it's decoupled and has a single purpose. You have different processing components that each have their own purpose. It has two main topologies, the mediator and the broker, and we'll take a look at those. All right, so this is the mediator topology for the the event driven. All right, so it's for when you have multiple steps within an event, and you need a central mediator to manage it. So some events happen in sequence, others can happen in parallel. Like say you have a credit card transaction, it needs to post a charge, withdraw money from a credit account and post it to the vendor collectible account. And Leonardo probably knows this sort of process very well. So then the vendors charge a transaction fee and the funds are held for some period of time, so the credit card processor can make sure the charge isn't challenged by the card owner, like the card might have been stolen or the vendor might have not provided the service, so they've got to go and roll that back. So some of these steps have to be done in order and others can be done in parallel, and the credit card processor has to be the one point where the event mediator manages everything. Otherwise, it's going to quickly become very complex, different processes trying to manage the order of things. So there are different kinds of events. There's your initial event will kick off a series of sequential events, and then you've got your processing event, and that's generated by the mediator, and that's sent to the specific event processors. So your event mediator receives an initial event off of like some event queue, and that kicks off a series of events that the mediator manages. And any asynchronous events, which are the ones that can be handled in parallel, they're passed to an event channel. And each event channel might be another event queue, depends on how big of a system you have, or it can handle the event directly and it'll kick off one or a series of events that need to happen sequentially. And so, yeah, this event mediator, it might be a Spring integration process, or if you've got a more complex orchestration, you'll use a business process execution language, BPEL. So you can use a BPEL engine running on a business process manager. Okay, so this is the mediator topology, and we'll see how that compares to the broker topology. So here's your broker topology. It's for when you want to chain a bunch of events together, but you don't really need a single mediator. It's for more simple event processing where you don't need a centralized manager Instead, you've got basically an event broker here in the middle. It manages all the event channels that are used in the event flow, something like ActiveMQ or HornIQ. Each event channel passes its events directly on to the appropriate processor. If there's a related secondary event that needs to happen, then the event channel will handle that as well. So say, for instance, a customer moves to a new address. The address information needs to be changed. You also need to consider any sales tax or value-added taxes, and the new address may have different shipping rates. And in some places, it's illegal to ship some items, so you need to make sure to check into that as well. And about the phone number, did that change? And is this a permanent address change or only temporary? All these things and lots of other things need to be considered and handled in different ways. There doesn't need to be a single event manager to handle all of it. Move event can just have a list of things that need to be handled, and the event channel can take care of it directly. Okay, so the trade-offs here, it's a very flexible and easily extendable pattern. It works well for large applications and small ones. The distributed approach makes it very scalable, and it's a high performance pattern. And since the different modules are asynchronous and independent, you can deploy just the parts that you need to that need to be updated. The downside is that it's kind of complex, and so the dev team needs to be trained up to develop it properly. Also, the distributed asynchronous nature makes it harder to test. All in all, it's a great pattern to use for a number of applications once you're familiar with it, and if your application lends itself to asynchronous distributed business rule processing. Okay, let's look at the microkernel architecture. That basically, there are two different types of microkernel. It's a core system, or two different parts to it. It's got a core system and a set of plugin module. If you're using an IDE, it probably follows a microkernel architecture. Let's take a look. So your core system, it only contains the minimal functionality that is needed to make the system operational. It handles your common business logic and any plugin management. And the plugin components will handle any specific complex functionality that's needed by the application. So it makes it very easy to extend and very flexible. The plugin components need to be effectively standalone. You want to minimize any communication between the plugins so that you don't have any dependency issues. The core system needs to know how to add in the plugin modules, and that's generally done through some sort of a registry. And that'll contain information about the plugin, its API, and the connection protocol that it uses to get running. You'd see this in using some web services. This web services definition language, Open Service Gateway Initiative, or any kind of a releasable product. Your Eclipse or IntelliJ, they have plugins. It's popular and it's easy to package it up and install it as a single product. Since the contracts between the plugin modules and the core system can have different levels of complexity, and those can change over time, it's important to keep in mind that you'll need some sort of a versioning mechanism in place from the beginning as you start building something along the lines for this architecture. So Now, one nice thing about this architectural pattern is that can be used as part of another pattern. If you have a larger system, and that part, it has a part that tends to grow in complexity, you can set that component up using a microkernel architecture. It's great for evolutionary design and incremental development, which you tend to have when you're doing TDD. You start with a core system and then add functions as the application evolves. And it's a good architecture to start with for a new project because it's very flexible and you only deploy the pieces that you need. And if it turns out this architecture doesn't meet your needs, you can very easily convert it into another kind of architectural pattern, which is a good thing. Since the business logic is mainly isolated in the plugins, the performance is very good. The only problem, it doesn't scale very well. As your plugins grow, the performance suffers. You may have noticed this if you've installed a bunch of plugins in Eclipse or something, that it tends to take forever to get it to go. And it can be complex to develop, so it can require some extra training for the development team. But this architecture is becoming more popular recently, with TDD becoming a more popular approach for developing software. So it's less likely to be a problem where the developers don't know how to do it. Okay, let's look at microservices. This is sort of the new sexy, and people are hoping it'll become the new silver bullet, perfect architecture for all purposes. Let's look at it and see where it's best used. One thing that's clear about microservices pattern, each component is where's my note here? Each component is a separately deployed unit. So rather than thinking about services within a microservices architecture, it's more helpful to think about individual service components. Each service component has one or more modules that handle a single function or an independent part of a larger application. So determining how granular that service component needs to be is the hardest part of implementing this kind of architecture, and it's also an important part of knowing how to do it properly. Another important concept about the microservice architecture, it's just distributed, meaning each service component is fully decoupled from any other component, and it's accessed solely through an API of some sort, like JMS or REST or RMI, or I don't know, do people still use SOAP? Anyway, so interestingly, this architecture evolved from other architecture patterns based on the needs that weren't being met by those patterns. I guess that's how any architectural pattern will develop. But so by its nature, it handles a lot of the shortcomings of architectural patterns. So the agile model of continuous delivery, where you require you need to be able to always be ready to deliver the application. So that required your monolithic application be able to break off autonomous chunks of the application that can be deployed independently of the rest of the application. So that started to move toward what's called a service-oriented architecture. And that was a helpful step forward, but it was complex and heavyweight, and it couldn't be used effectively for smaller applications. So the microservices address the complexity by simplifying the notion of a service, and it eliminates the heavyweight orchestration requirements that service-oriented architecture has. It simplifies the connectivity and access to the service components. So there's dozens of ways to implement this pattern. The most popular is this one that we have here, where you have a number of very fine-grained service components, hence microservices, and they have just a few business modules for handling specific business logic, and they're usually accessed by a REST-based interface through the API. Typical REST-based architectures tend to have more coarse-grained service components, and that limits the scalability. This is what the microservice architecture addresses. You know, keep it small, smaller than that too. Actually, maintaining microservices, a lot of times it's considered easier to just rewrite the microservice if you need to make a change or support some new functionality. It's easier to just rewrite it than to go and enhance an existing one. That's generally how small these services can be. Okay, so what are the trade-offs? Well, microservices are very extendable, and they can grow. They're very easy to test. They're scalable, and they're easy to develop and deploy. So what could go wrong? Well, the distributed nature of a microservice, it can cause problems with performance. Other things to consider: it's important to use the proper granularity for the service components. If your service components are too heavyweight, then they just start to grow, and then they're no longer microservices. On the other hand, if they're too fine-grained and you start having to orchestrate a lot of things, then you risk that becoming very complex and confusing. You're back with the service-oriented architecture. If you find that you need to add orchestration to your application to manage all the different service components, you'll just check to see if maybe they're too fine-grained and you need to combine a few of them. And in the same way, if you find that your microservices need to communicate with one another to process a single request, then maybe it's too fine-grained and you need to combine them. Of course, you want to minimize that so things don't grow too big. And if things start growing and you need to include more and more functionality in one place, maybe you just need to break things up. If you can't avoid either of those situations, then maybe you're just using the wrong architectural pattern. So the advantages of microservices architecture is that it overcomes a number of the limitations of the monolith and your service-oriented architecture. It's broken up into small, separate units, so it scales better, and it can more easily support continuous delivery. It also makes it possible to do real-time production deployments, so you're not having to shut things down for the weekend or longer. Project that I work with shuts down for a week to go and update the application. This is craziness. The whole point of the microservice is that you just update the pieces that you need in parallel. You'll probably have multiple instances of a microservice deployed, so you just update the one that you need. If that doesn't work, you roll it back out, or if it does work, you slowly replace the other microservices. And that is pretty much impossible to do with a layered architecture. Now, one other thing to consider: since the architecture is distributed, it shares some of the complexity concerns of the event-driven architecture pattern. So just one other thing to keep in mind. All right. Finally, we've got the space-based architecture, also known as the cloud architecture. So most web-based applications follow a pattern where the request will go from the browser and then to the application server and then to the database. And that works great for small applications, but as the scalability needs to increase, you start running into bottlenecks. First, you're going to run into bottlenecks at the web service layer. And so to resolve that, you're going to create more web services and distribute those out to handle your web request. And then your application server is going to have trouble keeping up with all the requests. So you're going to have to distribute that out as well, and finally get to the database. And you may not be able to distribute your database, or it'll be very expensive to do that. So that tends to be the bottleneck that keeps the performance having difficulties. So generally, we will just be throwing more hardware at the problem, and you end up with this inverted triangle of distributed systems. So you're going to have a bunch of web services at the top, or web servers at the top, and then application servers, and then a database server that's holding everything up. So it's really hard to solve very large scalability problems. Well, cloud architecture to the rescue. It's all about scaling. It's based on the concept of having shared memory. So the high scalability, you get that by getting rid of this centralized database and replace it with these replicated in-memory data grids. There's your data right there. The application data is replicated between the different processing units, and it's kept in sync so that all the data is the same for every processing unit. The processing units can be brought online or taken down as the user load level change. And since we don't have a centralized database to slow it down, you've effectively got infinite scalability, which is really cool. The two main pieces of the architecture, your processing unit and your virtualized middleware. The processing unit has all your application components, your UI and your business logic, and the application functionality is distributed however it needs to be among the various processing units. The processing unit also holds the replication engine that replicates the changes for the data. Any changes that this processing unit makes will to the data will instantly be propagated out to the other processing units. Now, this virtualized middleware, it handles housekeeping and communication. Okay, it's got components that handle data synchronization and request handling. We're going to discuss that in just a minute. First, let's focus on the processing unit. So the magic of the space-based architecture pattern lies in the virtualized middleware components in the in-memory data grid. Okay. This is a typical processing unit architecture. It's got your application modules, your in-memory data grid, come on, and your asynchronous persistence store for any failover, and your data replication engine. It's going to be communicating with the other processing units to make sure that all the data stays in sync. Okay. Now your virtualized middleware, it's essentially the controller for the architecture. It manages any requests, sessions, data replication, distributed request processing, process unit deployment. And there's four main architecture components. You got your messaging, your data processing grids, and your deployment manager. Your messaging grid, it manages the input requests and the session information. It receives a request, determines which active processing unit is available to handle the request, and passes that on to the processing unit. The data grid, it's probably the most important part of this. since that's where our bottleneck tends to be. That will interact with the data replication engine for each processing unit. And that manages the replication when the data changes on the processing unit. So it's critical to make sure that each processing unit has the same data set. So it's a very high performance module. The processing grid, it manages your distributed request processing if you've got multiple processing units. So it may or may not be there if you've only got a single processing unit. If there needs to be coordination between the processing units, you know, say you got order processing or customer processing, this processing grid will manage it all. And finally, you got your deployment manager, and that manages your the basically starting up and shutting down your processing units, depending on what the load is like. So this component continually monitors the load conditions, starts up a new processing unit or shuts one down. And it's a critical component for making sure that it's scalable. Okay, so as you can see, this is a really complex architecture pattern. It's very expensive to implement. It's great for websites that have loads that go up and down, you know, like eBay, that sort of thing, where you have people, you'll get a whole bunch of things happening at once for some given time, and then things will slow down again. It's good for, it's not good for your large scale systems that have a big relational database application to maintain. It's very maintainable. Performance is great. And like I said, it's all about scaling. By definition, it's easy to deploy because it's constantly spinning up and down the different processing modules. And these benefits make it hard to test and hard to develop for. It takes a lot of training to get it done right, and it's easy to do it wrong. It's easy to end up wasting a lot of resources. I'm sure we've all heard the horror stories of some AWS application that blew through tens of thousands of dollars of CPU time for a weekend that nobody was even paying attention to it. So you don't have to use one of the big cloud providers to do this. There are ways to host cloud-based services locally. That's known as a platform as a service. Of course, since each of the big vendors have different strengths and weaknesses, you really need to know the needs of your application before you choose a vendor. Keep in mind that changing a cloud hosting vendor is about as easy as changing a relational database. Frankly, I've never heard of a product that changed their database. So, you pick a database. I'm going to use an Oracle database. You're not going to go to a SQL Server. That's just same thing. If you're choosing AWS, you're not going to go to Google. They just make sure to lock you in. Okay, so I hope this was helpful. This is a sort of a thumbnail comparison of each of the different architectural patterns. Every architecture has trade-offs. So there's no silver bullet that's going to solve every problem. You need to determine the needs of the problem that your customer has, and from that you'll choose the proper solution. Okay, like I said, you're going to have to think, use your experience and your judgment to determine what architectural pattern you should use, and that's just the way it is. So, any questions, comments, concerns?
Scott, I have a comment too.
Okay.
Relative to the when you have multiple modules, one big issue I had this year is to reuse code. Sometimes
Right.
we have a module that does a specific thing, and we need another module to do a very similar thing, but we cannot put it in the same component. We need to create another
Right.
component. And
Yeah.
in this case, what that I did this year is to basically copy, paste, and
Right.
rewrite one or two lines to make a second deploy. This
Right.
is a bad thing, or there is a better way to do.
Well, I mean, that's really, because I'm assuming you've got a microservices architecture that you're doing this for, right? And that's in order to maintain the performance necessary for a microservices architecture, that sort of thing will be necessary sometimes. If you find you're doing that a lot, then that probably suggests that you need to create another service component that has the the shared code in it. But you know, there are trade-offs, and you know, that's just one of the trade-offs that happens with this particular architecture. The fact that you feel icky doing it, that's a good thing.
Mm.
So, but yeah, you know, sometimes you can, what you can do is sort of have a library for the code that needs to be used in different components, and have those components talk to the library. But that's, you know, again, you're just creating another component. So,
Yeah. Okay. But the perform in our case it's we did in this manner is because the benefits that you speak about
right,
the positive the positive the
right,
positive things, yes, but the worst thing that I yes the advantage,
yes,
but
yes,
for me the main disadvantage is to the rewrite of code.
yeah, that's a good point. So, you know, that's, again, it's that's why you're the professional. That's you kind of have to determine, you know, like I was saying, that the you can start to have problems of granularity here. You've got to choose the right granularity. If it's too granular,
Yeah.
then it's going to be a hassle to maintain it. If it's not granular enough, then you start developing a big ball of mud in the corner here, which is a problem. So yeah, it's something you have to stay on top of, and that's what you're called to do as a profession.
Yeah.
That's why we're here. We're trying to become the tech lead, and that's what the tech lead needs to be able to do. Okay.
That's it.
Yep. Anything else?
Have a comment. I would like to share my experience with two different architectures. So the first, the layered architecture, and the second is the microservices architecture, and the relationship between these two. Okay, recently in my company, there were some discussions regarding the most important system of the company, the system that is responsible to produce most of the revenue for the enterprise. You know, and this system is essentially based on a layered architecture. The ideas how the system was designed is exactly what you have described here with this layered architecture. And one of the things that you said, and I totally agree, is that the layered architecture will eventually lead to a monolith. And this is exactly the problem that we are facing in our organization. We have this, in the beginning, the layered architecture is good because the code base is not so huge. Maybe there are not so many teams dealing with the same code base. So in the beginning, it's something manageable. It's a piece of software that the complexity is something that you can handle. Okay. But what I started to observe in this company is that as the code base starts to grow and more responsibilities and more features were added to that system, and with that more teams started to touch the code, the complexity started to get out of control. Okay, so and then eventually the system became the monolith that we have today, and basically is a big mouth, but it's hard to add new features. It's hard to change. For example, when we have new developers, the learning curve to understand how to contribute to the code base, this learning curve is high because well, there's a lot of noise surrounding the thing that you are interested in. And all this thing led the discussions about, okay, how can we solve this problem? How can we tackle this situation? So the idea is to starve the monolith. The idea is to try to decrease the size of the monolith. And what's the main strategy for this thing? Microservices architecture. So people start to discuss, hey, why not we extract parts of the system into microservices, okay? And actually, I would like to ask you a question on that regard, Scott, because this is the path that I can see that my company is heading. So they identified some modules, some core services, okay, and this, let's say this responsibilities, these main features, they are distributed across different teams, okay, so they are mapping the boundaries, let's say like that, the boundaries between the system, and the idea is to extract this first, map the boundaries, map the modules in the monolith, okay? Because also once you do that, the idea is to extract this thing into a microservice. Okay, and by doing that, you can decrease the complexity of the monolith, and then you have a manageable, a smaller piece of software that you can have. Okay, what's your opinion about this strategy? Okay. Extracting components, extracting modules from a monolith, layered based architecture into a microservices system. Do you think that this is a good strategy? Have you seen this before? It works? What's your advice? How to conduct this to make sure that this undertaking will be successful?
That is considered to be the ideal approach to creating microservices. That if you start creating microservices from the beginning, you may not know how they should be created. So ideally, you start with a monolith, and then as it starts to grow and things get to be hard to manage, you start finding parts that you can break off into the microservices. And then you've got an easily maintainable piece right there. And then you're not having a bunch of different microservices that maybe you're not sure if it's too granular or it's not granular enough. You know, it's easier to determine how granular it needs to be because you know what it depends on in the monolith, and you can isolate everything that this particular microservice needs and separate it out. So yeah, that is considered to be the in the industry the ideal approach to creating microservices.
So would you agree that the natural system evolution would be to, for example, first start as a layered architecture, right? Because of the advantage that you put, it's simple, you can validate your idea, you can create something, produce some value. And then as the systems evolve, the natural or the logical path for managing the complexity would be to go to the either microservices architecture or choose something else that can help you to tackle the complexity. So would you agree that that would be one of the ways that the system can evolve. So we start with, to summarize, we start with layered architecture, then we progress, and then we mutate this layered based system into microservices and something else. That would be one of the approaches to handle the evolution of the system.
Well, that's generally the approach that is taken. The alternative is to start with your microkernel architecture, which is, I mean, it's designed to be flexible, and it's, it's, well, okay. I mean, basically, you can easily turn a plugin into a microservice, or a set of microservices, because I mean, it's already isolated. So, so having this kind of an architecture, if your application lends itself to it, would be a good way to start. That, or again, the layered architecture is generally where most people start because, excuse me, it's more simple. It's just you don't really have to train people up as much. Pretty much everybody understands the model view controller, right? Here's your model, here's your view, and here's your controller in the middle. And so, you know, if you, that's been in the industry for decades, and everybody is reasonably familiar with it. So that's kind of how it goes.
How about one question on the microkernel? This architecture is somehow new for me. So when you were explaining the microkernel architecture, if I'm not mistaken, you gave as example the IDE. Okay,
Yeah.
so we have the IDE. For example, the IDE is the core system, and then we have the plugins of the IDE. So
right.
Like, for example, IntelliJ. IntelliJ, the core system, and then we can provide more functionality. We can provide more features by adding plugins to the system. Okay.
Right.
This concept, it's very clear for me on with this kind of application. The question to you is, what about backend systems? Like, for example, you have a system that has an API that provide different functionalities and things like that. So it is not for example, a desktop application or IID, but instead it's a backend service that run as a process in some server, you know. So how would handle, how would implement this kind of architecture? Because one thing that come to my mind is how I can approach this plugin company. Should, for example, I deploy them as separate units, deploy the deployment units, or should they be part of the same deployment unit, but for example, I should separate them as modules or different components? So how you do handle that in developing and applying this kind of architecture for backend applications, backend services?
Well, the backend may not be the ideal place to implement this kind of an architecture. It depends on the kind of work the backend does. If you're, you know, if it's, I'm trying to think, if you've got like different, say you're doing, I don't know, credit card processing, and you've got different credit card processors to interact with, you could break off the interactions with each different credit card processor into a separate plugin. And then you can have another plugin for taking whatever processing and managing that in the as far as the customer accounts are concerned, that sort of thing. If you can break it up like that, you know, if you could separate out the different pieces of functionality, but then you're already starting to move into a microservices type of situation. So, but the sort of the thing about this microservice architecture is that, like I said, you can use it as a part of another architecture. So if you've got a layered architecture, or you've got a monolithic back-end system, you can break out pieces in the back end into a microservices type situation in preparation to moving towards a microservice. Is that what it is? Microkernel into a microservice. So anyhow, but it really, it would depend on the needs of your system and what it looks like.
Interesting. Yeah, yes, I agree that maybe the back end applications may not be the best scenario, but I think that there may be some advantage in this idea, because when I see this plugins like, for example, modules. So you can have the core,
Right.
the core system as the part of the system that has the core functionality, and then we can create these different modules that represent the boundaries of the application, and I believe that this kind of approach can help us to, in the future, if you need to decouple, if you needed to go to something more distributed, like a microservice architecture. I think that this idea of having the core system in the central and surrounding the core system will have this design based on modules. I believe that this can help us in the future to decouple and extract and move to a microservice architecture. So maybe this is one of the values that they can get from this idea, from the microkernel. Maybe using viewing these plugin components as modules that you can attach to the core system.
Yes,
that's how I see. But that's it. So thank you. Very, very cool. Very nice explanation, and I really like it, the layered, because I'm doing some research about different architectures, and the explanation about layered was very comprehensive, because I did some research on the internet, and the things that I found, they are very shallow, and I could see that you went really deep into explaining the details and also the advantage and the disadvantage. So very nice presentation. Thank you, Scott.
Okay, sure. Thank you. Yeah, and I guess there are some architecture books that I should recommend. I don't think I have any. All my architecture books are ebooks right now, so I will add that to this presentation. I will put a list in the course for see if that would be helpful for you. Okay. All righty then. Well, I know that Leonardo is taking time away from his family to hang out with us, so I will not extend this longer than it needs to be, but I appreciate y'all being here, and I will get this up for recording for up on the or on the website. A little spent, so all right, we'll let y'all have a great weekend, and we'll look forward to talking to y'all again next week.
Thank you, Scott.
Thank you, Scott.
Weekend too. Have a nice weekend, David.
To you too, Leonardo. Have a nice week ahead. See you guys. Bye.
All right. Bye.
Bye.